Alright, this is the second part to the first video that I uploaded today. This video is on full wave rectifiers. And if you haven't watched my first video on half wave rectifiers, I recommend you watch that one first, because we discuss the function of a diode, and that's going to be helpful in understanding the concepts presented in this video. So let's talk about full wave rectifiers. Now, a full wave rectifier is very, very similar to a half wave rectifier. Just thinking about the name, we have a full wave rectifier here compared to a half wave. So we have twice as many waves as the half wave. So if the half wave has a certain amount of waves, the full wave will have twice as many waves. So just from the name, we can kind of get an idea of what's going on. Now, a full wave rectifier is more preferred over a half wave rectifier because the full wave rectifier takes advantage of both alternating cycles within the alternating current voltage source and takes that voltage and that current and applies it throughout the load in each cycle. So that might sound a little bit confusing, but think about it like this. I've drawn a full wave rectifier here. Now, the important part that you gotta recognize is that electrons will be flowing through the load. So think about the electron flow through the load. I'm going to talk about a positive full wave cycle, full wave rectifier, and I'm going to talk about a negative full wave rectifier. And hopefully the concept will be clear. Alright. Right here I've drawn a simplified full wave rectifier, and basically it's doing the same thing, but you have to kind of visualize what's going on. How the electrons are flowing through, which way the current is restricted, etc. So if we think about a alternating current that's being applied here, if we think about the positive cycle, electrons will flow this way, come to this junction here, and then since we have a forward-based diode here, electrons will not be able to flow here, meaning I'll get a current flowing through my load. That's the first positive half cycle. Now the second part is going to be when the negative half cycle is applied. Yeah, my current will be allowed to go through here because it's forward biased, because the diode here is forward biased. But when I reach this junction, electrons will not be able to flow through this wire. They'll have to come back down. So if you're seeing, for each cycle that's being applied, the positive or the negative, I'm getting the same amount of current in each cycle, as opposed to a half wave rectifier where I'm only getting one cycle at a time. So if it's a half wave, I get one cycle, then I have to wait because the electron flow in the other direction is restricted, and then I have to wait, and then it comes back. But the full wave rectifier, for both cycles, I'm getting current flow throughout my load. So that's very important. So here I've tried to show how the voltages will match up. So if we look at an AC signal, positive and negative, this is my AC signal, and we're looking what's happening when it goes through this positive full wave rectifier. This is my AC source. This is one cycle, stops. And this is, we're looking at, remember, we're paying attention to the load. So I have a positive half cycle that's applied. Electrons are flowing through here, they stop at this junction, go through my load. Awesome. I get a positive wave. Then, in the other cycle, electrons come through here. Again, they pass through my load because they won't go through this wire because of that diode. So, like that. So this became this, and this stayed as is. this became this. Sorry, my diagram is not the best. And this became this. And that repeats forever, or as long as you are applying the AC load. Down here, so this one was a positive. Let's discuss a negative full wave rectifier. So in this case, there's going to be a negative that's going to pull electrons from the ground through the load, and that's for my first cycle. For the next cycle, same thing. When the electricity goes this way, it's pulling the electrons out of the ground towards the negative terminal. And this is what we call a negative full wave rectifier. So in this case, we're converting the positive cycle to a negative, and the negative stays negative. So this, it might be a hard concept for you to grasp. For me, it was kind of hard. But you have to think of, the best way that I can describe looking at this is think about how the electrons would flow through the load. So remember, electrons are always going to flow from positive to negative. So if I have a negative terminal, when in my negative full wave rectifier, my electrons want to flow this way, as opposed to the positive, where I have a positive source here coming down and flowing towards the ground. So you have to visualize what's happening in your wires, and that's really, really important. So if we discuss the formulas, these are again taken straight from the textbook. You'll notice that for our DC load voltage average, we have a difference of 2. We have twice as many waves occurring in our DC, pulsating DC voltage, that is our output. Why is that? Well, when I started off this video, you guys told me yourself that you have twice as many waves. If you have a full wave versus a half wave, you're going to get twice as many waves. That's why the 2 is here. All the other formulas are the same except for the PIV, which is your peak inverse voltage. We're going to subtract one diode when we're taking that into account. All the other formulas are exactly the same, and I hope this makes a little bit more sense. I might go over a full wave rectifier that might come on the exam, which is a bridge rectifier, which has some benefits. But for now, I think I've covered both. So I covered half wave and full wave rectifiers. If you're still having trouble, take a look in the textbook and make sure you can kind of visualize the electron flow. I also recommend, if you can go online and model each circuit, model each simulation, that would be best for you as well. So I hope you learned something, and I'll see you if I make another video.